They're filling up. Hi, everyone. Thanks for joining us today. That's him letting a few more people in. My name is Jennifer. I'm the marketing manager here at EGI. And today, this is our first webinar of the fall semester. And I would like to introduce Dr. Nate Moodie. He is you're still a postdoctoral research associate here at the U, correct, Nate?
No, now I've graduated. I'm now a research assistant professor.
Now you're a research assistant professor. Got
Yeah.
it. So Dr. Moodie, a research professor here at the U, he's going to give this webinar and we'll leave some time for questions at the end. So you can unmute yourself or put them in the chat box if you'd like. And then after this webinar will go on YouTube, so you can share it later if you need to. Okay, Dr. Moodie, I will hand it off over to you.
Thanks, Jennifer. I appreciate that. Dr. Nathan Moodie. Yeah, I'm happy to be here to present some work that I've done over the past number of years. And some of you may have seen some of this before. Some of it may look a little familiar. I did some very similar webinar last year, but I have done a lot of additional work on this that I'm excited to present. But I'm here to present what I call an integrated approach to derive relative permeability from capillary pressure. And let me share my PowerPoint, get started. And this was initially work that I started with coding this in Excel and doing a lot of work with spreadsheets to make these curves, and have now created a full web app that does the work, and getting ready to publish that to live so that people can use that. And so I'm gonna first go through a little outline here. I'm going to go through just kind of the theory and background of the method development, where it came from, then go into just a kind of a brief description of kind of what the method is and how it works, and then show some of the older fitting results that I did and simulator curves that I developed using this method, and then we'll go into kind of a web app demonstration. And so really this method for deriving relative permeability curves from capillary pressure data all came about really because I wanted to fill gaps in simulators, because I do numerical simulation, and it's difficult to find good relative permeability curves and capillary pressure curves for your numerical simulators. And a lot of times I started off just using the default ones in the Tough 2 manual, because I started off with Tough 2. And noticed a lot in the literature that people did the same thing. It kind of, the relative permeability curve was an afterthought. And really that comes down to, it's an expensive piece of data to gather. Laboratory testing can be anywhere from like 30,000 to 90,000 or more to get relative permeability curves. And with that, it's like 30,000 per relative permeability curve, not for a whole suite of them. And so it's really expensive data to gather. And you need core from downhole, and you need a significant piece of core. So you need, at least 1.5 inch by 3 inch core to do this. And I've seen some talks now in the past couple of years where researchers at these laboratories that test for it really recommend that you have much bigger core, up to 6 inches and longer, which can be very difficult and very expensive to gather. And capillary pressure, on the other hand, can be measured on core chips and small pieces of core, and is relatively cheap, a couple $1,000 for a mercury injection capillary test. And so develop this method, and I'll go into the theory here that really built on some work done by previous researchers to understand or to develop relative permeability from capillary pressure. So just to give you a little kind of the backgrounds, the fundamentals, so we're kind of all on the same page. I mean, capillary pressure really is just the pressure between two fluids in a thin tube or pore network. And so you have your pressure of your let me get my little laser pointer up here. There we go. So you have your pressure of your non-wetting fluid, in this case air, and your pressure of your wetting fluid, in this case water, and a meniscus between them. And that pressure across that interface is your capillary pressure. Now we can measure this using the interfacial tension between these two fluids, the contact angle between this meniscus and the pore wall, and then the radius of the tube or the pore network. And using this formula here, which is your non-wetting minus your wetting, you come up with your capillary pressure. This is really a fundamental formula developed, many, many years ago. And so that really leads into, kind of what relative permeability is, because this capillary pressure really is the basis of what relative permeability is. And that is, in essence, it is just the ratio of the pore space that each fluid is going to be able to access within a pore network or a thin tube. And this illustration here really sums that up, where we have gas, oil, and water. We have three phases here, and you can see the water wets to the walls of the pore network. Then the oil is kind of intermediate wet and fills in between those, but doesn't fill in this, the thinnest of the walls. And then the gas is the most non-wetting and just forms a bubble within the main pore and doesn't really go through the pore throats. And so relative permeability is a way to describe this in your numerical simulators. And it really has to do with kind of the properties of your matrix. There's which fluid actually wets against this wall. Is it the water? Is it the oil? Is it the gas? Most of the time, it's not the gas. The tension between these, the interfacial tension between these different fluids, which depends on fluid density, viscosity, things like that. So how did we get here? Back in 1949, Purcell derived a method for determining permeability by pushing mercury through a porous media sample. And he would measure the capillary pressure from that, and was able to then derive or calculate relative permeability. And so incremental pressure changes in this fancy apparatus with a little hand crank on it, he was able to come up with the steps that gave you the saturation and the capillary pressure, and then understanding your interfacial tension and your contact angle, and using this formula here, which this is tortuosity and this is porosity, you can calculate what the permeability of your sample is. And he also derived this for converting your laboratory testing data, your mercury air data from your capillary pressure machine here, into your reservoir of interest, which in the case we're talking about here would be brine and CO2. It could be oil and water. It could be oil and CO2, things like that. And you can use this formula to calculate that. Then in the 50s, a couple of groups actually, we'll focus on what Fatt and Deisker did, but a couple of groups developed a way to actually calculate your relative permeability. And so they did that from the idea that if you have a sample that's saturated with water, say, and you flow a second fluid through there, you're always going to leave immobile water coating the grains. And this fluid will only impact part of the pore network or fill part of the pore network. And so that would be your effective permeability of this second fluid phase that flowed through there. And so they would calculate your effective permeability using the same formula, but instead of 0 saturation to full saturation at 1, they would go to this saturation where you still had some immobile water in there. And it would be less than full saturation of your sample. And so that would be the effective permeability of whatever fluid phase that you flowed through there. And then relative permeability is just effective phase permeability over what we call intrinsic, or the bulk permeability of the sample, or the true permeability of the sample, which is just this ratio. And so you can just take these two formulas, you put them over each other, this whole term drops out, and you're just left with these two integrals. And so from kind of this basic understanding of how you can calculate relative permeability, I just kind of discretized this formula, and because we're dealing with discrete data, and so we need a way to calculate discrete time steps or discrete pressure steps. And so just using a triangular rule, took the integral and turned it into this discrete formula. And this forms really the basis of the method for deriving relative permeability. here, in this case, water, from these capillary pressure uh, measurements, capillary pressure versus saturation measurements. One of the other, or a couple of the other pieces of critical data that you also need to understand in order to get a good relative permeability curve for your numerical simulator is you have to figure out where these endpoints are. And so you can relate your capillary pressure, shown in this lower chart here, to your relative permeability. And so there's a couple key points on this chart. So as your capillary pressure, as you reduce your water saturation to closer to zero, you'll get to a point where that water isn't going to move anymore, and your capillary pressure curve will start to approach vertical, or if you take the derivative of that, 90 degrees. And that's a point where you're reaching your irreducible water saturation. And that's a point on your relative permeability curve where you'd be no longer flowing any more of your water or two-phase fluids. It would just be, in this case, clean oil or clean gas. There's also a point where you do transition from two-phase flow, in this case oil water, to clean oil, and that's lower down on this curve where you hit this critical water saturation point, where you now hit the point where you're not going to move any more of that immobile water. And it's above your irreducible saturation point. And that's where on this curve, you're going to go from two-phase flow into single-phase flow. And then on the other end, if you already have gas in the system, you flow the water back in, you're going to have a point where gas is going to be stuck in that pore network and not want to move out. And you're going to transition from two-phase flow into single-phase, wetting phase flow here, where you're going to have immobile gas. And that's kind of this point on your capillary pressure curve, where you have your maximum water saturation that you can have after first contact with your non-wetting phase flow. So those are some critical points for the water saturation. Now to relate those to maximum relative permeability. So if this is your maximum water saturation, then this is your maximum relative permeability in the two-phase flow area. Now, if you're able to then kind of dissolve out that gas over time, you can get to full unity and full maximum relative permeability of one. Same way on the non-wetting side, where under two-phase flow, where you transition from two-phase flow to single-phase flow, this would be your maximum relative permeability of your non-wetting phase. But if you're able to dry that core out through continuous flow of your second fluid here, in this case oil, you could reach up to here to full unity and one. And so these points are critical to understand and be able to pick out. And so I'm going to use this information and these relationships to come up with the critical points in the method that I developed. So here I'll go through the method here, show you kind of using some real laboratory data, what points you need, what data you need to develop a relative permeability curve from this mercury intrusion capillary pressure. And so this is a sample that we got from the San Juan Basin, from the Entrada sandstone. And this is its mercury intrusion capillary pressure curve right here. And so the first data that you need is you need to understand, or you need to have the porosity and the permeability of the sample. And if you do a mercury intrusion capillary pressure test or MICP test, you'll end up with this data. And so this data is a part of the method. And then you'll need to know your interfacial tension data, because that's critical. So you can convert your mercury curve here into your simulator curve for capillary pressure. And you need to know your contact angle for this portion of the formula. And that way you can then convert this data here into a capillary pressure curve that you can use in your simulator. And then these exponents in your relative permeability formula here, you have this B exponent here and this C exponent here, effective saturation exponent. These need to be derived from fitting this method to laboratory measured data. Been able to do that with quite a bit of laboratory measured data. And so these values that you see here came from fitting the method to many different sandstones, both from the San Juan Basin as well as sandstones from the literature. There was a couple researchers, Benyon and Bakhtu, and I think I'm saying his last name right, and Krever, that had done some testing where they'd done both capillary pressure testing and relative permeability testing on basically sister samples or samples that were very close to each other in properties. So, for example, Berea sandstone, which can be thought of as kind of a standard, and it did multiple testing on that. And so using that data, these are, if you don't have any kind of measured rel perm to fit these curves through, you can just use these as good stand-ins. And then if you're using this method to actually fit to laboratory data, then these maximum and minimum water saturations and maximum relative permeabilities can come directly from your samples that you tested. But generally, you're not going to have that data. You're going to have a capillary pressure curve, and you're going to need to make the relative permeability. And that's where the algorithm that I've designed can come up with some of these numbers based on those relationships that I showed in the previous slide and picking those points on this curve. So we'll go through picking those points. And by the way, I didn't mention this, but this can be done for both 2 phases and 3 phases. So you can do this in say, geologic carbon storage reservoir, or you can do this in an oil and gas reservoir that you want to do, say, CO2 flooding or CO2 EOR in that, and be able to come up with relative permeability curves for your simulator for both of those scenarios. So the first point that's relatively easy to pick, because this shape here is in almost all the sandstone curves that I've seen. Anything with high permeability and porosity generally has this type of curve to it. When you start getting relative permeability in shales, or sorry, capillary pressure measurements in shales, sometimes these curves can look a lot different than this. But if we're looking generally in a reservoir, this point's really easy to pick. And this is as your curve here rolls over, you want to pick where you kind of change from concave to convex. And that would be kind of that maximum water saturation, or this would be your residual gas. On the other end, it becomes more difficult. This irreducible saturation point actually is fairly easy to pick, similar to this, because this is where the curve starts to go vertical, or where your angle of your first derivative approaches 90 degrees. And this one is actually fairly straightforward to calculate as well. It gives you very broad relative permeability curves. And sometimes that doesn't match what maybe the laboratory data would be showing you, or if you think you want to pick that critical saturation point. So this was the greatest challenge for me to try and figure out, how do we do this? How do we pick this point? And this, depending on the curve, is the most uncertain point that we pick. Just as a caveat, this is one where sometimes the algorithm won't pick the right point, and you'll have to go in and manually pick the right point where you think, so, oh, maybe it's over here instead of where it picked it here. But we've kind of, using the algorithm, defined this point as where you start to see the greatest change in angle in your derivative. That just means where you go from kind of this flat area and the curve starts ramping up towards irreducible saturation. And that's where your critical saturation is. But you can have curves, anybody that looks at mercury intrusion curves can see that sometimes you have bumpy data, and that can throw off the algorithm. Still haven't figured out a good way to address that part of it, other than to just let the user select that point if the algorithm did get it correct. The maximum relative permeability is a little bit, this is another tricky one to come up with. I have automated ways, and then same with this water saturation. There's also ways that if the automated ways don't work, you can go back in and hand pick them. You don't like it. So the first point is actually picked the maximum effective or wetting phase relative permeability is picked here at the same point as your maximum water saturation. But the non-wetting phase is more difficult. And instead of picking it at the same point as your critical saturation, I looked at this method that Swanson used, where he theorized that if you plot your MICP data on a log-log chart of bulk volume versus pressure, where the two trend lines, the vertical trend line and a trend line in the main part of your data, intersect each other, the line normal to that, we'll pick a point on the curve where he theorized you were getting the bulk flow of fluid through your sample. And I chose that as basically the non-wetting effective permeability. And it seemed to do a good job of picking this point with most of these curves, picking this non-wetting phase effective permeability, and it would match up fairly well with when we would run this against experimental data. So these are the two curves that I developed for the two-phase method for the wetting and the non-wetting phase and your capillary pressure conversion. And so first thing that kind of you need to do is you swap this so that you're looking at water saturation versus this is mercury saturation down here. So you basically just swap this curve. And then what I'm showing here, of course, this is the Entrada sandstone capillary pressure, but this is also the relative permeability data that we measured on this same sample or one real close to it. It was within the same depth interval that we grabbed these samples. And so using this method, I wanted to fit to this. So if I want to fit directly, I can use the endpoints of the data and get a really nice match. I haven't adjusted in this particular instance here, I haven't adjusted the curvatures or the B and the C exponents to change the curve values. But even just using the standards that I've come up with, it fits really well. You can mess with these curvature values and get a much, much closer fit. And I have actually a slide in just a second that shows that. Then if we want to apply the method where we're looking at saturation endpoint that's up here, where the curve starts to go vertical, you get this nice broad curve. But as you can tell, it doesn't really match with your laboratory data. But if you choose the other method where it picks this point as your critical saturation point, then you have a much closer match to what your data is. And so under most cases, I choose this point, this critical saturation point when developing relative permeability curves and see that it matches pretty well with what the laboratory data gives you. This is just to give you an idea. This is the range of curves that overlaid on each other. I'll show you that, especially in this gas curve or the non-wetting phase curves. Big difference here. And this difference between this curve and this curve is going to make a big difference in your numerical simulation. And so, not a caveat that you need to choose these very carefully, because if you choose this curve, but your data shows this curve, you're going to end up giving much different answers or predictions on storage volumes and the ability of the fluid to flow through the reservoir. And so another thing to point out is you can see that this laboratory fitted curve is really low maximum rel perm. And that's because the laboratory data ended here. This would make for kind of a pretty terrible relative permeability curve for your simulator if you wanted to just use this directly. So I always caution against just using laboratory data directly. I think most researchers would caution that you don't want to do that. You need to upscale these curves to an endpoint that you would likely expect within your reservoir, which should be much higher than 0.11 or up closer to 0.6 here, 0.55. So this method also is a way for you to take and upscale this laboratory data so you can fit your curves to the laboratory data, then use the B and C that fit the data the best to then generate the curve for your simulator. So let's show a couple examples here of fitted data, and this was back using the Excel. This was before I coded this into Python and then built a web app out of it. And using Excel, I could get this is the sum of squares. So good as a fit between my predicted and laboratory data. Really, really good. This is an excellent fit, and it gives me these B and C exponents for my algorithm right there. And I'm able to do this with, these are Entrada samples, additional samples. So this is the one I've been showing throughout the presentation. But these are additional samples that we took of the Entrada sandstone in that same San Juan Basin area. And again, able to get really, really good fits and come up with these fitting values for B and C that go into go into the method. So I just click through those. And one thing to note, these two samples have basically linear relative permeability for the gas phase on both of these. And these two have these really, especially this one, it's just basically linear, and then it just steps up. So kind of some interesting data, and I don't have any information on why these samples acted in this way. Do you see this in other laboratory data? Then you can see some that have these really beautiful curves go up on both ways. I don't have any of that. This is the bluff sandstone in the same area of the San Juan Basin, but here we only had the capillary pressure curve, no relative permeability data, and used the method to develop the simulator curve for that. And I used the generic fitting parameters for sandstone that I've developed. And this is for the reservoir. Bluff is a reservoir rock. Now you can also use this for seal rock, where you're basically going to be unable to do a standard relative permeability test because the rock is so tight, and it's going to be very difficult and very time consuming to try and flow fluid through those very tight pores. And you can see this is the capillary pressure curve here. Does not look like any of the others. I'll click back. So that one, or curves that look like this, right? That's this curve, very different. Big, slow kind of change from concave into flat, basically. And so here, kind of the method's going to predict a very tight relative permeability curve with lots of residual, both non-wetting and wetting phase, which is probably what you're going to see within a seal rock, if you're able to even get two phases into that seal rock pore network. This isn't the fracture network that you may have in the seal rock. This would be in the pore network, just as a caveat. So sometimes in the simulators, you do see the second phase intrude into the very bottom of your seal rock, the very bottom cell of that. And so it may be of interest for the researcher to have a relative permeability curve for their seal rocks. And so this method can do that using just the capillary pressure curve. So from here, I would like to transition to demonstrate the web app. Should do escape this. Go there. There we go. And pull up the web app. So here is my front page. I've got a little write-up about relative permeability method that I developed here. You get a little write-up about it, abstract from a manuscript that I posted on that, example curve, and a great plume generated by AI. I did a pretty good job with this of putting a second fluid into a primary fluid. Anytime I tried to get it to do some sort of like two-phase flow in a core, it was a mess. AI still has a long way to go in generating curves or pictures. So we'll log in here. First, let's do, well, I had Bob and Slick Willie. Let's do Donald Trump. I think he wants to do some testing here. Oh, sorry, login. No, we will register a new gentleman here. Sorry, we'll register a new gentleman. Mr. Donald Trump 11 because he's top. Let's see. See if I can remember that password, and then White House. Oops. Trump at whitehouse.com. And then he's of course at the White House. Oh, I already have it here. He's at the White House. So we'll register him. He can do some testing now. We'll add him into my password manager so I don't have to do this again. Okay. So we'll log in now. So now you're back at that same landing page, but now you have some options for developing these relative perm curves and showing you if you've been here before and this isn't your first registration, you'll have how many results you've done and what types of methods. This empirical methods, I'm still developing this particular module. I'm hoping to get it done by now, but this data fitting module was throwing errors up until about 6 p.m. last night. So hopefully this goes through smoothly. So we'll start off, we'll do a two-phase fitting. And so it brings you to this screen and we'll select some data. Let's do a Berea sandstone. That's a good one. We'll fit a Berea. So that should bring up, yep, here's your data, your input data. You have your capillary pressure and your saturation and a comma separated file. We'll pick a project name. Since this is new, he doesn't have a project name, so we'll call this web app showcase. We'll give our sample a name. Sandstone, the file a name. Let's call it 301. And then we can choose how many intervals do we want in our curve. The more intervals, the kind of basically the more data you have in there. Sometimes that can give you a smoother looking curve. For the simulator, I think we'll go with 10, make it a little finer. Oh, unprepared. I don't remember what the porosity and the permeability of this Berea sample is, but let's say we'll say it has a 40 millidarcy, and we'll give it 15% porosity. Here's your CO2 water interfacial tension and contact angle. Let's increase that. We'll make that contact angle 10 degrees for the CO2 water. And then your mercury and air, which you probably shouldn't change. These are basically industry standard values. And so just leave those. And then we'll leave the standard values here, these generic values. And you can put any notes down here that you want. Now, where do we want to define our relative permeability values? Do you want to let the algorithm do it, or do we want to enter a value? It gives you that choice. We'll let the algorithm do it here. Same way here. The algorithm will give it a choice. And then where do we want to pick this minimum saturation? Do we want it where the curve reaches vertical or roughly hits 90 degrees? Or do we want it where we basically have the maximum change in angle, which is the critical water saturation? So we'll choose the critical water saturation here. And then we can have a couple options. And then you also you have an option to pick this from a chart or enter the values directly. So if you're fitting to laboratory data, you may want to enter this value directly because you have that data, upscaling from laboratory data. If you want to pick it from the chart, a chart will show up here. In fact, why don't we do that? We'll pick it from the chart. We'll pick both of these from the chart. This chart will show up. Well, I'll just show you that. Actually, I want to highlight what the algorithm does first. But this chart will show up if you want to pick it from the chart. We'll go ahead and we'll use this first derivative. And this point here is the first rollover point in the data. And then the only other bit that you can choose, how do you want the algorithm to extrapolate beyond your minimum and maximum water saturations? Do you want to keep the relative permeability flat there? Or do you want to specify values, either anything above what it picks? Generally, if you select this, you would use extrapolate it up to 1 there. What we'll do is we'll keep this at the maximum saturation, or the maximum values predicted by the method. And then this is the Swanson chart here that will determine where your effective non-wetting phase relative permeability is. And you need to pick 2 points on this chart to pick this trend line here. This trend line's picked automatically. You'll see that in the results here. And so once you pick these 2 points, run the model. Here's our relative permeability curves for your simulator, the capillary pressure curves for your simulator. This is a chart of the data. It has now saved the data to a database that I'll show. I'll go to the results tab and show that we can download that data. Here's your original capillary pressure curve. Here's your simulator curve. Show you the difference in pressure there. These are the constants that you selected and or entered. So you have that information, as well as, oh, this is the effective permeability chart, and it broke. Well, I got a bug here. Whenever you do something live, it always breaks on you. I did this probably 7 or 8 times yesterday, and this all looked good. So not sure what happened here. I'll have to dive into why in the world it did that. So this should plot the chart and show you that. Well, I can actually pull up some other data that I have and show you that. And then here's the chart from Swanson's method with, this is the trend line that we chose. Here's the vertical trend line, the line normal to that, and that picks that point for your effective gas phase permeability, which is, in this case, 25.8 millidarcies. And so that over the bulk permeability of your sample, which we chose was 40 millidarcies, then you get the maximum effective permeability for the gas phase, which is here, 6.4. So, and then you have some of the endpoints that it calculated, the maximum, minimum, or the maximum wetting phase and non-wetting phase permeabilities, relative permeabilities, the minimum and maximum water saturations, your KEG values or your effective permeability values that are used to calculate these. What was the max? That was 40, what we entered. And this was your tortuosity value that you did. So there's a rundown of 2-phase. We can do the same thing for 3-phase. Go here for 3-phase. We'll select one of these Morrow sandstones. We'll do the 58. I've done this one a number of times. I know this one works. Knock out. Select that. Now that we've entered a project name, it's now saved this project name. So we'll go ahead and select that. Give it a name. And it's done 58. It's at sample 58. 8. So the case name is, if you notice, it comes up on the top of all your charts. And this is what your file name is going to be when you go into when you download this data, it'll call that. So I try and keep them basically in line with the MICP data that I'm uploading, so I know what samples I have. Here we'll keep it at 15, so we have more values. I don't remember. Again, I didn't write down this information, and so we'll leave these default here. Say this is a low permeability sandstone sample. Actually, let's increase this to, let's say it's 10 millidarcies. And then here again, your oil, water, here's your interfacial tensions and contact angles for your fluid phases. And this, now you have oil, water, and gas, oil. And so since we're doing 3 phases, you're going to have 2 sets of contact angles and interfacial tensions, as well as your laboratory data. And then you're also going to have 2 sets of the B exponents and C exponents, because we have one for your oil water curves and one for your gas oil curves. So we'll leave that. So, you see. And then a little slightly expanded here as well, where you're going to choose, do I want to enter my values here, or do I want to let the algorithm pick them? Again, we'll let the algorithm pick them. Here, let's highlight the chart. So we'll pick the chart for both of these, and we'll go ahead and select the data from the chart. And we'll leave this as the whatever the algorithm picks. So we'll pick our curve here. And then we need to pick our 2 points. And so here you can clearly see we have boom, this point here, this break. So maybe right about here is where our minimum water saturation is going to be. And then this point's a little difficult, kind of flat almost all the way. We'll pick kind of, say that's the curvature, and we'll pick this point here. This is going to give us a very broad relative permeability curve, like the model, and it worked. Here's your simulated curve for your oil and water. We have a fairly low oil maximum relative permeability. So depending on your knowledge of these samples, you may want to go back and go, this isn't good. I want to pick one up here and do a better curve. Gas probably looks okay for this particular sample. And then you have two simulator curves for your capillary pressure plotted against your input data. And again, those are these two curves. So this is your oil water capillary pressure for your simulator, and this is your gas oil for your simulator. Or actually, it's really gas total liquid. It's oil plus residual water is what you have in this. So I have liquid saturation here instead of oil saturation. Again, here's your input data that you put into the simulator. Here, the effective permeability chart worked mostly. They plotted both oil and water and gas and oil on top of each other. They have the same effective permeability. I have to double check if this is actually correct or if I've got a bug here too on the chart. And then your Swanson curve, as well as the data that the algorithm came up with for your endpoints and stuff. And then so all of this is then exported into your results chart. So now we can see we have two sets of results. So we want to see, like, oh, let's look at that Berea one again. So we can view that, take us back here. We can see this data. We can export this data. That'll bring up a zip file. And that will have, we can go ahead and extract that, and that will have our simulator curves in it. So we'll have, here's our relative permeability curve. Let's bring up Notepad. This is just in a comma separated curve. So this isn't going to be able to port directly into your simulation here, but this is the data, water saturation, relative permeability of water, gas, and your capillary pressure. You can put this into Excel or into a word editor and modify this so that it fits with whatever simulator that you're trying to apply this to. As well as now you have your parameters file here. These are the parameters that went into the method to show you those. This is the input data, the MICP data, your saturation of mercury, capillary pressure of your test data, as well as the converted capillary pressure of your reservoir here. As well as it output the charts that we were looking at. This is your effective permeability calculation. So it outputs all the data so you can go back and check and make sure that it all makes sense. There isn't any problems. I wonder if this is actually, I don't have a good viewer. I'm working off of a server right now here on campus. And so it doesn't have a good view. Like it doesn't have a Windows viewer. Maybe this will pull up. Yeah, it did pull. Okay. So I do have a bit. So, and then here's the charts. So you can see a couple of the different charts that you saw on the page. And so that exports all of that data for you. Go back over here. And say, oh boy, I didn't like this Mara one. Yeah, go ahead and delete it. Get rid of that. Now I want to highlight the data fitting, which I was struggling with until just like 6 p.m. last night. So you have a number of different options based on what you want to do to fit this data. You can use the method I've just highlighted and gone through to fit the data, come up with that. But say you're working with the Tough2 simulator. Well, you can't put tabular data into the Tough2 simulator easily. But you have Corey's curve, Brooks-Corey, Van Genuchten, Grant's, Fat and Klinkoff curves. You have these functions in, say, the Tough2 simulator. Well, you can fit your laboratory data now to this. Let's pick Corey's curve, because this will be the simplest one to look at. and come up with what the endpoints that you need to add into Tough 2 to get it to match as best as possible to your laboratory data. So we'll use the Entradas here. This is the only laboratory data I have uploaded, but we use its Entrada sample. We'll call it Entrada 51810. I'm going to look at the time here. Okay, I'll be done after this. And I could take questions because it looks like I've been talking a lot. So then we'll go fit. It's the file. Let's see. Yeah, web app showcase. More notes here. And we can choose the outputs, or we can have the fitting algorithm just pick the two endpoints from the data. So I'll go ahead and choose them this time to showcase that. You can choose these two endpoints that you want. Say you want to restrict your fitting and not to this curve up here to here or one of these other points. You can do that. Gives you that option. We'll select that and we'll run the fit. And so this is the fitting of it gives you your sum of squares fit error, and then the two endpoints that you would put into your Tough 2 here. So if I only highlight one more real quick, let's use bank inductive because this is a very popular one. People use this all the time with same data. Open that. Say fit 2. I'll select the existing one, ignore the notes. Here we'll add in a starting lambda or the bank inductant, and I won't choose any of the points. We'll let it fit to the whole thing. And so here's what Van Conductant looks like to get the best fit possible. This has a much better fit error than the Corey's curve because you're able to adjust your lambda. Here's the lambda that you would want to use in your simulator in your Tough 2 simulator. So that's the highlight. Definitely willing to take any questions now that anybody has. I left about 10 minutes for questions. Let me go ahead and log out and I'll log back in as the administrator here. And as administrator, I have the ability to get rid of Donald Trump or Bob Barker or whatever user that I want. That's another bit. If you're built the code, now you have this functionality. So, but yeah, any questions from the audience?
And feel free to unmute yourself if you have a question.
Well, I don't have a question, but I'm impressed, Nate. This is really cool work. I'm excited that you've done this.
Thanks, Dan.
Hi, can I ask a question, please?
Yes, please.
Okay. Thank you very much. Interesting work. I have more than one question, but let me start with the first one. We know mercury injection data is oil drainage mode. Let's talk oil water reservoir, let's say. Dynamic modeling or reservoir modeling will require imbibition curves, not the drainage curves. How are you going to deal with this? Where you have not only pore geometry effect, but also wettability effects that are affecting the fluid flow.
So that was dealt with by picking. Let me bring back up the presentation here. Slide it over on the screen. That was dealt with when you're able to choose these points here and here. So now you're assuming that this part of your curve is your residual. So this would have been after first contact. So on your imbibition curve. So you would have this and here where you would have that. And so that's how the method deals with the fact that, yeah, that mercury intrusion is, basically you're pushing, mercury through air. So you don't really have that second bound fluid in the pores necessarily. So that's how the method deals with that, is that you take this into account. And so if you think that your reservoir is not going to be able to, say, push all the way to full water saturation, and then your relative permeability isn't going to get all the way up to 1 here, but you'll have a lower relative permeability and this amount of trapped gas. Similar on the other side, if it's, say, oil here, or you have this amount of trapped water. So, in this point, it's 45% trapped water here. So that's how you deal with that.
Yeah, I'm talking about imbibition. Let's say water wet versus oil wet case, or mixed wet versus oil wet case. All of these will have impact on the imbibition mechanism, on how the imbibition is happening, about the trapping of the oil in the imbibition case. So, like with oil wet, let's say it's lower residual oil saturation. With water wet, it should be higher residual oil saturation. How do you define this?
So in a mercury injection test, if that's all the data you have, you don't have that. You don't have that information. And so you're already dealing with extremely limited information. And so really, if you have a lot of that information, you wouldn't necessarily use this method to derive the relative permeability curves, because you already have a lot more information than this. This is really designed for if you're dealing with situations where all you have is capillary pressure data, and you have to come up with some plausible relative permeability for your numerical simulator. Right. And so this is a way to deal with basically the least amount of data possible without just using an empirical formulation and literature values. But I do know what you're saying, that I don't have this in the web app, but in the Excel version when I initially built this, I also had the ability to, with changing these your contact angles, you can tune the wettability, so you could be in more of a mixed wet situation where your curves are close to 90, or where your values, your contact angle values are close to 90 degrees, or where you could be in an oil wet situation where these contact angles would be over 90 degrees, right? And so by doing that, you're able to kind of tune that. So if you're in an oil wet situation versus a water wet situation under 3-phase conditions, you're able to tune that with the contact angles here. But that really, all of that just tunes the capillary pressure curves for your simulator. Relative permeability, when you calculate that, so these overlap each other. Let's click down to here. There's no interfacial tension or contact angle in these formulas. So the relative permeability is agnostic to the wetting situation using this method.
Okay, thank you.
Yeah, you're welcome.
Okay. Hi, Nathan. Thank you for this presentation. Can you go back to the slide number 9? Actually, no, the number 7. Sorry, 7. 7. Yeah.
This one here?
Yeah. Here, how did you define the SW max? Means the SOR or SGR. Yeah. So given that the mercury injection is only drainage mode, so how did you end up with this value? How are you able to define this?
Well, Dolan in 1982, this is where I got this relationship from. He has this real definitive book on porous fluid flow and porous media, and he had argued that this point on your curve is what's going to determine the residual non-wetting phase saturation based on, even though, like you said, that this is effectively drainage curve, right? So,
Yeah,
but
but this
he's
varies from sample to sample. Sorry, this varies from sample to sample. Yeah?
very much so. This shape of this curve varies very much from sample to sample. Sometimes this could be very long. Sometimes you're almost a straight line. And I did show, whoops, sorry, I did show one where further down in the I think it was for the one of the samples. It's basically a straight line. So this is very difficult to find. You don't see this rollover. So yeah, this varies. This is kind of an idealized curve where he says, okay, as you move from this concave to convex, what you're doing is filling up the major pore space in there and leaving the small pores untouched. And so he argued that these small pores would be your residual non-wetting phase. And as you force more mercury in there, you have this plateau where you're basically pushing the fluid through the major pore networks. And then here you start impacting the really small pores within there. And then you get to the point where you can't force the mercury into any more of the pore space within there. And that's the irreducible saturation. And so he was arguing that this point here fits with this point here where you have your residual non-wetting phase after first contact, right? After imbibition.
Mhm. Okay, thank you.
Yeah. And again, this is really just, if you have more data, like laboratory data and more data than just capillary pressure curves, you use that data to really help refine, okay, where are these points and stuff like that. But the beauty of this method is if I, as the simulator, as the guy that needs to come up with the answers for the storage capacity and the fluid flow, and we've never drilled a well, and we have legacy capillary pressure data from a handful of core chips, I've got to come up with a relative curve to go into that so that we can move forward with the project and tell them, okay, what's our area of review for our class 6 permit, but we haven't drilled the well yet. So this is a way to get to that data when you have very limited in what you got out of the ground. And believe me, I wish that under lots of circumstances that we had more core out of the ground and more data so that we could really refine these endpoints to understand the drainage versus imbibition and where these points really are. But there were many times when I just have basically no data except maybe a capillary pressure curve. And you're asked to run some extensive fluid flow simulation and give the team an answer on storage capacity and size of the plume and all of that. And your relative perm curve makes a huge difference on that answer. So that's really what pushed me to come up with this. How do we deal with just almost no data?
Are there any more questions before we wrap up? Okay.
So real quick, Jennifer, before we wrap up, we're right now pushing to kind of get the last bugs in the web app ironed out and a couple more things added. I have one more module as well as some help information that I want to add to help users. And then we'll publish this live. And through EGI, we'll share the link through the EGI marketing material. And that way, any researchers here in the near future that want to use this when they have very little data to generate rel perm curves and capillary pressure curves for the simulators, we're able to do so. So we're working towards that. Hopefully, in the next month or two, we'll have this live. Maybe Jennifer, we can shout from the rooftops when that happens.
That's great, Nate. Yes, definitely we will.
Thank you all for coming. I appreciate the opportunity. Have a great evening or afternoon.